everyone. My name is Shrimai Prabhumoye, and I primarily work on controlling style, content, and structure in natural language generation, and that is what I'm going to be talking about today. So we constantly author text, be it on social media platforms or personal or professional documents like OneNote or Google Docs, or opinions in the form of blogs, or even newspaper or Wikipedia articles. But very few of the times we actually generate new content. We commonly borrow information from different sources and try to recast it to fit our application. For example, you may read a newspaper article and then decide to write a Facebook post on it, in which case you're going to borrow the content from newspaper article and you're going to write the Facebook post in your own style and in your own structure. But you may also decide to write a blog post on it, in which case the structure will be different. And that's why today in my talk, I'm going to talk about these three attributes: the style, content, and structure. So at the end of my PhD, I envision to build a model which can control all three of them together. And this is the main difference between this model and the pre-trained large models that you have today. Because in those cases, you cannot control for these various attributes that you would like to control for. You want to be able to control for the content, that is what you want to generate; style, which is how you want to generate something, how do you want to say something; and structure is when you want to generate something in a coherent manner or in a particular order. So first is style, that is the surface level realization of the intent of what you want to say. So do you want to say something in a polite manner, like do you have any code that we can look at, or in an impolite manner, like any code, or do I have to guess at how you did it? And next is content. You want to be able to control for the information that you are generating. So in most of the generative models that are used today, especially for dialogue, they tend to hallucinate the facts that they are generating. And that's why this is an excerpt of a conversation from one of my other works on document-grounded generation, where we collected human-human dialogues, and the humans were supposed to talk about things that are only given in the document, which is on the right side. So as you can see in this case, the user 1 had access to this document, and user 2 is supposed to converse freely. And as you can see, the user 1 has actually used information that is there in the document, like who are the actors that acted in this movie, or what ratings did it get on Rotten Tomatoes, etc. So you can envision building a chatbot which can then use this document as an external source of information and use that to generate the responses. And last is structure, that is you want to be able to generate something in a coherent fashion. So we know that newspapers, for example, have an inverted pyramid kind of structure, where they start with the most important information within the first 1 or 2 sentences. It will tell you things like what, how, where, and when about that particular event in the first 2 sentences itself. And then it will diverge in the main body, that is the main argument of that news article, or the story of the news article, or the controversy that it is discussing. Here it will give you the juicy bits like who said what to whom, pictures, background, details, etc. And then finally there's the tail part to the newspaper article, which is like other interesting facts or other editorials related to this particular topic that you can read. And if you look at structure in this way, then almost every written text does have some structure. Like your essays that you write for SATs, they have a structure. The recommendation letters that professors write, they have a structure. Wikipedia articles have a structure. And even those jokes that your uncle tells at all the family reunion parties, that has a structure. It has a beginning, then there's a point of the story which is revealed, and then there is this awkward pause that is there, after which there's a moment where there's some important detail which was purposefully concealed is revealed, and then finally it has to end with you had to be there. And now if you can see that if you change the ordering of any of this, like if you have the you had to be there part before the awkward pause, it will not have the same effect. So it has to be done in a certain order. So what are the applications of such a model, that if you can control for the style, the content, and the structure, then where can you use it to where all these three are applicable? So one of the famous applications is, of course, chatbots, because you want to be able to generate responses in the style of the person with whom you're talking for better effect. You want to be able to also generate factful information, factful responses, because we don't want to be like Tay, right? And you want to be able to generate dialogues in a particular structure, strategize them correctly so that you don't mess up with the dialogue. So here I'll show you example of each of these, where each of these attributes are important and what could go wrong if you're not able to do these things correctly. So if I ask the bot, if I tell my bot, I have a talk today to present, and the bot can just say best of luck, which is a very bland, it is a correct response, but it's a very bland response. And so this does not go with the style of the user that is saying it. But if the bot knew that this particular user is a Star Wars fan, let's say, then it could say, may the force be with you. And it will have like a better effect, like the user will be more satisfied with this bot. Then if I say, hey, have you watched Avengers Endgame? And the bot says, yeah, I loved Bradley Cooper in it. So this is, as you know, it's wrong content, because this is something it can just hallucinate this. It has to say something about it loved a particular actor in this movie, but it didn't generate the correct actor. And if it said like, yeah, I loved Robert Downey in it, then that makes more sense. And again, the last is structure. So if I say, hey, have you watched Avengers Endgame? And it says, yeah, I loved the movie. And I say, can you tell me the story? And then it has the correct content here. The entire story over here is correct, but it's in a jumbled order. So if I tell, okay, Thor killed Thanos, and then Iron Man stole Infinity Stones back from Thanos and used it to disintegrate Thanos and his army at the cost of his life, and then Hulk travels to New York in 2012 and gets the time stone, and then 5 years later. So you can imagine how this can just go wrong, and it becomes, the information is still correct. So it's generated contentful information, but it's not in the correct structure. So wrong structure, and it has to do it in the correct order of things. Some of the other applications of, if you can control all three of them, then you can use it for writing assistance tools, like you can make your emails sound more formal, more polite. You can use it in OneNote or Google Docs kind of scenarios, where if you're writing an essay, it can help you to structure that essay, or if you give it some external sources, that even it can do fact correction for you, and you can also control for the style of the essay that you're writing. But more importantly, it can just be used for content generation in general. Like if I give you relevant documents and say, generate a website for me or generate a wiki article for me, then can you do that using that? Because I'm telling you the style, I'm telling you the structure, and I'm giving you the information. So for example, a few years back, Facebook decided to generate pages of people who have a Wikipedia article but don't have a Facebook account. And this is how my advisor's page looks like on Facebook, Alan Black. He doesn't have an account on Facebook. Not only is the picture not aligned correctly, but as you can see, the page is completely bland. Like the first two sentences of the about part is literally copied from Wikipedia. But if only they could control for style, content, and structure, then they could even generate posts using the papers that Alan has published in the style that Alan has written, because you can detect that from his papers. And you can even do it in his voice, because his voice is freely available online. So the overview of my talk is going to be, I'm going to talk about my work on the three of them, the three attributes: style, content, and structure. And so first I'll talk about my work on style transfer. So style transfer is the task of rephrasing the text to contain some specific stylistic properties without changing the intent or affect within the context. For example, shut up, the video is about to start, is something that you would say to a friend at a party setting. But please be quiet, the video will begin shortly, is something that you will say in a more formal setting when you're having a meeting. And some of the specific applications of style transfer task is that you can use it for anonymization. That is, instead of transferring from male to female type of sentence, you can use it to anonymize the author attributes like gender or age. You can also use it to generate demographically balanced data sets for a lot of downstream tasks for which currently the data sets are pretty skewed. So our goal was to create a representation that is devoid of style but holds the meaning of the input sentence. And in this journey, we faced a few challenges. The main one was to separate out the content from the style. The other challenges in this task is that we don't have any parallel data at all. So you don't have the mapping between the sentence. The movie was very long, which is a very direct way of saying something, and its indirect version, that is, I entered the theater in the bloom of youth and emerged with a family of field mice living in my long white mustache, which is like an indirect way of saying that the movie was very long. And also remember that style is very subtle. There's a lot of discussion and debate going on in the community about what should be considered as style and what not. And it is also very hard to detect when you're in a particular style or not. So our solution for some of these problems was back translation, that is translating an English sentence to a pivot language and then back to English, that is back translation. And this reduces the stylistic properties of the sentence. It helps in grounding the meaning of the input sentence. It creates a representation that is independent of the generative model, and the representation is also agnostic to the style task. And I'm going to explain the last two parts, what I mean by being agnostic to the style task and being independent of the generative model. So the pipeline looks something like this. You have a machine translation system, in this case English to French. You can use any pivot language of your choice. And this is trained on a completely different parallel data set for MT, which has nothing to do with your style transfer task. You take this MT system, and then you take your style specific corpus. You translate the English sentence to French. You then take the back translation system, that is the MT system going from French to English, and then you only take the encoder of this system, and then you encode the French sentence to get the representation Z. Now, as you can see, this Z is completely independent of the style task. You can have as many style tasks as you want, and how you reach this Z is independent of that. It is also not dependent on the generative model, because I have not trained any generative model so far. Like the style transfer generative model is going to come after this point. So this is the representation that I was talking about. From here you can train, this remains fixed, and from here you can train two separate generative models for each of the two styles. So in this case, I thank you, Representative Wisłowski is a democratic sentence, and that gets transferred to I'm praying for you, sir, in the Republican version of it. So my train pipeline is that you have this fixed representation Z, and from there you have two separate generative models for each of the two styles, and you also have a classifier which gives you a feedback whether the generated sentence actually belongs to that desired style or not. And this error is backpropagated to my generative models. So the loss function for my generative models is a weighted combination of the reconstruction loss and the classifier loss. And as you can see right here, that these two losses are competitive in nature, because the reconstruction loss tries to reconstruct the exact same sentence as the input, whereas the classifier loss tries to change some things in that so that it fits the desired style. We have used sequence to sequence framework for this model. We focused on these three style tasks: gender, which has labels male, female; political slant, which has labels Republican and Democratic; and sentiment modification task, which has labels negative and positive. And so we first, how do we evaluate our models is that we evaluate it on 3 metrics. First is the style transfer accuracy, and this is evaluated using a pre-trained classifier. So you test the classification accuracy of the generated sentences using this classifier for the desired label. And these are the accuracies of my classifier. So as you can see, the classifier does do pretty good. So here are the results for our style transfer accuracy metric. As you can see, the blue is the baseline and green is our model. And as you can see, for the 2 tasks of political slant,
a liberal perspective and a conservative perspective, you're also presumably changing its content most, if not all, of the time. So how is this an instance of style?
So the kind of things we wanted to see was the example that I gave, where they have very different ways of greeting. Like I'm generally Republicans say I'm praying for you, sir, for example, and Democrats say more of thank you, dash, etc. So we wanted to see that kind of those kind of style transfers, but I agree that at times in like at times between these styles, like the content can change, and so the answer for that would be that it depends on your downstream task for which you're using the style transfer technique at all. Like for example, even in a pizza ordering system, if I change the number of pizzas, like when I'm going from one style to the other, then that's a very like wrong thing to do. So the application matters a lot. So but if you were to give a review and your if you change the number of pizzas in your review and the sentiment of the review remains the same, then it's fine that you change the content. So it really depends on what you're using your style transfer for. So yeah, it would be same for political slant. And so in this case, I'm going to talk more about why for gender we see this drop. But the second important metric is preservation of meaning, because you can have 100% style transfer accuracy if you generated good when you were going from negative to positive, but it would fail because that's not a good transfer. You've lost the content of it, and that's why we do preservation of meaning metric, where we do A/B testing. That is, users are shown 2 generated sentences by models A and B without in a randomized way, and they also can choose no preference. So we ask the human judges questions like which transferred sentence is semantically equivalent to the source sentence with an opposite sentiment in case of the sentiment transfer task, or which transferred sentence maintains the same semantic intent of the source sentence while changing the political position for the political slant part. So as you can see, for the 2 tasks of gender and political slant, our model performed better than the baseline, but in all 3 cases, definitely the no preference was the most popular option, because there's a lot of scope for improvement for all of these models. But specifically for gender, as you can see, our model performed much better than even the no preference option. And that's the discussion that I wanted to have, that as we saw before, the loss that our generators get trained on are competitive losses, where one tries to improve the meaning preservation and the other tries to improve the style transfer accuracy. And for our model, especially in the gender task, even if the style transfer accuracy was low for that task, but it did much better in terms of meaning preservation, and this is the kind of behavior that you want to see in your model. Also, we would like to point out that sentiment modification task is actually not a well-suited task for style transfer, because as Mohit just mentioned, that when you go from one sentiment to the other, you inherently change the meaning of that sentence. And I'm going to give more examples of this in the next few slides. And the last metric on which we evaluate our models is fluency. The human judges are asked to annotate it on a scale of 1 to 4, 1 being unreadable and 4 being perfect. As you can see, across all tasks, our model performed much better in terms of fluency, and especially the difference is more accurate or acute in when you're generating longer sentences, like between 15 and 30 tokens, then the difference is much larger. And here are some examples of the style transfer. So the first one is the source style, and the second one is the target style. So this is the examples for gender when you're changing from male to female and female to male. These are examples for the political slant transfer. So as you can see, for the political slant, we wanted to see things like, I will continue praying for you and the decisions made by our government, versus I will continue to fight for you and the rest of our democracy. So not a lot of content that is changed there. And for the sentiment modification task, for example, if you see like the positive to negative, where the food is excellent and the service is exceptional, gets changed to food is horrible and the service is terrible. And in this case, even if you exchange the adjectives and say that the food is terrible and the service is horrible, it would still be fine. So it's hard to evaluate whether that would be the correct style transfer, or this is the correct style transfer. So do people have questions on style? I'm done talking about style, and then I'll move to the content part. Yeah, you, whoever. Yeah, go first.
So for all the results, you use French as language.
Yeah.
But you're assuming that all information about gender and these things are discarded when you translate from English to French?
We feel it is reduced. It is not going to zero. We know that.
Couldn't you just use the encoder part of the English language? Why do you need to translate it to French and then?
More like to ground the meaning. So there are already a lot of experiments that are done which used autoencoders, and even I did experiments with autoencoders, and that was not giving good results because it was doing more like copying from one to the other. Yeah, there was something more that was needed to kind of get the actual meaning of the sentence.
I have two questions.
Yeah.
One is the examples that you just showed, it seems like there were very minimal changes from one style to another. I imagine a very high precision approach to some lexicon-based replacement would be pretty good on your evaluations, right? And probably for most sentences, you may not want to change anything. There's nothing like think or spray, right? So did you think about that?
Did I compare my model with the lexicon? There were papers on that, but not all the examples were I believe the sentiment one is the one which is, I would say, the closest one, which the lexicon exchange could get you good accuracy. But things like save yourselves the huge headaches, you are gets changed to you're going to be disappointed. Things like that you're not going to see. So we did see things that are more than just changing one word or two words or something like that.
I suppose the more you change the sentence, the worse your meaning preservation.
Yes, that is true.
Okay.
That is.
Yeah, so second question regarding the meaning preservation evaluation. So it seems like, if I understood correctly, you did this evaluation by ranking the two competing systems. So to say, which one better preserved the meaning?
Not ranking, it was A/B testing of human judges. So we showed them both of the generated output in a random order, and they had to pick which one is closest to the reference in
Right,
meaning.
there was no, just given this generated sentence and the original sentence, how well is the meaning preserved? Like a paraphrase style evaluation?
Like,
That's kind of hard to
yeah, like you're saying more like on a scale of 1 to 5, how close is it to the original sentence, etc. Yes.
It has to preserve the meaning, but also
Change, exactly. So
it seems like a hard task for mechanical cursors.
exactly, yeah. So that's why we, in fact, went with the A/B testing approach, because there you had to, it's a little more clear there that they have to just pick one or two, or they can pick no preference, which could mean both are equally bad or both are equally good. Yeah, yeah. So next I will talk about my work on content transfer. So the current AI editorial assistant tools help you in correcting the form of what you've written, like the grammar or even the style. But there is currently no editorial assistance which tells you whether what you have written is factually correct or not. And that's why we wanted to focus on controlling the content. For example, this example, which is from one of the grammar correcting tools, will help you to correct errors of this form where graduate should be graduating, etc. But there is currently no tool which will help you to correct if I wrote after graduating from Carnegie Mellon University, Obama worked in Chicago, that it should be after graduating from Columbia University, Obama worked in Chicago. There's no assistance, there are no tools which will help you with that, and that's why we wanted to focus on this. We wanted to see how information is recast when you're writing these documents. So our task is that if you have a Wikipedia article, let's say on the monkey selfie copyright dispute, and there's already some information that is there existing in that Wikipedia article, but now a new update happens, a new event occurs. For example, the initial reports said that the monkey clicked the picture itself, but later the photographers later clarified that it accidentally clicked on the camera when this photographer was trying to shoo away other monkeys, etc. And so, as you can see, there's a reference link that is left when this edit was made. And so our task is, can you generate this update, that is the part in orange, given the existing Wikipedia article which is in yellow, and this news article from which this update was generated, which is the part in green. So to reiterate our task, if you have a curated context, a curated text or some context that already exists on a particular topic, and now a new document comes in relevant to this curated text on the same topic, then can you generate the update, and only the update, given the curated text and the document. So we have designed this task to perform content transfer from an unstructured source of information, and we have released a huge data set to do this task. So some of the applications of this particular content transfer task is that you can use it to update software documentation. If whenever a new software requirement comes in, then can you generate this update for the software documentation? For inbox summarization, like if you were maintaining a summary of a particular thread that's going on, then now if a new email comes in about the same thread or the same topic, then can you update that summary? Can you update legal documents whenever new laws or amendments to the laws are passed? And can you update Wikipedia articles every time a new event occurs which is relevant to that particular Wikipedia article? So for our dataset creation process, we used Wikipedia because that's a very rich and huge source of information, and it also has a lot of links that link you back to where this information came from. So we parse Wikipedia article, and then the moment we hit a reference link, the sentence before the reference link becomes the update, and 3 sentences before that becomes the context. We have set the window size to be 3, but you can have it as long as you want. Also, the links are constrained to belong to 86 domains, and this was done to maintain the credibility of the sources, but you can also have longer lists of domains, etc. So once you have the context and the update, you take this link and try to search it on Common Crawl, and you extract the HTML of this news article. And then you process this HTML to get the plain text of the news article. And then so eventually you're left with the tuples of the news article mapped to the Wikipedia context, mapped to the update which actually came from the news article. And we have a total size of 636,000 instances of such kind. So on the modeling side, we have experimented with both generative models and extractive models. All the generative models use global attention, For all of these models are very simplistic models, and they were primarily there to kind of infer whether context helps you in this grounded generation process or not. So first we have the context agnostic model, and this one is a baseline model because it does not have access to the context. It just has the newspaper article. It encodes it in a sequence to sequence manner, and this encoded vector is used to generate the update. Then we have the context informed model, where we concatenate the Wikipedia context to the news article, and we encode this concatenated sequence to get the vector of that entire sequence, and we generate the update based on this concatenated vector. And for the context responsive model, we have two separate encoders, one to encode the news article and the other to encode the Wikipedia context. And the update generation process is conditioned on both of these because the encoded vector of the Wikipedia context is used as an additional vector to each time step of your word embedding when you're decoding. Whereas the encoded vector of the news article is used to initialize the state of the decoder. And in this way, the update generation process is conditioned on both of them. For extractive models as well, we had simplistic models. So the sum basic model, which is based on unigram probabilities, what it does is that it gives a score to each sentence based on some aggregation function of the probabilities of the tokens that belong to that sentence, and then it picks the sentence which has the highest score. It then discounts the probabilities of the tokens that belong to this selected sentence so that the same sentence is not selected again. And it continues this process until your summary length is exhausted. We also made this sum basic model into a context informed sum basic. This was to see whether context actually helps you or not. So how we do it is that you calculate unigram probabilities over both the Wikipedia context as well as the news article, and then you first discount the probabilities of the tokens that belong to the Wikipedia context. So now the token probabilities are aware of what information was there in the Wikipedia context, and then the probabilities that are there after this discounting process is what we use to score the sentences and select the sentence. The oracle is used like to establish an upper limit attainable by any extractive model. This is so because it's a cheating model. We use the same metric, which is Rouge, both to select a sentence with the highest score for Rouge as well as to eventually give a score to this model, oracle model. So the first evaluation metric, automated evaluation, is Rouge. We also present Meteor and Blue numbers in our paper, which are consistent with Rouge-L. As you can see, the generative models perform much better than the extractive models. In general, the models which are aware of the context perform much better than the models which are not aware of the context, so you can't treat this task as a simple summarization task. The context-informed generative model had the highest score. The oracle model gets a score of close to 30 on a scale of 100, which tells you that this task cannot be solved using extractive techniques alone. We also perform relative human evaluation. So the first is close to reference, which measures how accurately the generated sentence is, how close is it to the reference update. So we ask the annotators the question, which system output is closest in meaning to the reference update, and we show the annotators the reference update, the generated sentences by the two models, the context agnostic model and the context informed model, and they also have the third option of choosing neither. And the other one is coherent to the content, and this is because the information that is there in the reference update may not be the only salient information that is there in the news article which fits this Wikipedia context. And to reduce the reference bias of the annotators, we have this second evaluation, we ask the question, which system output is more accurate relative to the background information given in the snippet of the article. Here we don't show the reference update to the annotators at all. We only show the news article and the Wikipedia context and the two generated updates. And as you can see, for both of these tasks, the context informed model performs much better than the context agnostic model, although the neither option is chosen most number of times because there's a lot of scope for improvement for these models. We also perform absolute quality evaluations using the DUC 2007 guidelines, where the human annotators are asked to annotate the generated sentences on a scale of 1 to 5, 1 being very poor and 5 being very good, on these 5 metrics of grammar, non-redundancy, referential quality, focus, structure, and coherence. And as you can see, on all of these metrics, the context-informed model performs much better than the context-agnostic model. Yeah. Yeah, to be honest, we have tried to look into it. We don't have a very clear answer to why grammar is affected, but we have shown a qualitative evaluation section in our paper where we find out that the model which was not using context had a lot of repetitions in that in the generations, and that could be the reason why people marked it lower for grammar. So here are some examples compared to the reference update, the ones that were generated by the context-informed model. And as you can see, it does get most of the things correct. It gets dates wrong sometimes, and it doesn't know when to perform coreference resolution. It performs coreference resolution correctly, but it doesn't know when to do it. So do you have any questions about this part of the talk? Yeah.
May I ask why in the context reference model, why do you use the previous part of the wiki as the input to the university?
How do I use it?
Why do you use it to every input of the university?
It's just another way of conditioning the generation on the context, the Wikipedia context. So the goal is to include this, the goal of the model is actually to find a diff between the news article and the Wikipedia article, because you don't want to repeat the information. You don't want to generate information that is already there in the Wikipedia article. Because there might be some kind of overlap between the wiki article and the news article, and you don't want to repeat information, and that's why you want to find this diff, that what is the new information, what is the novel information that's there in this news article, and which connects to the Wikipedia article, and you want to generate that, and that's why we use these models to condition on both of them. With what model? In the human eval. Like, because one of them was agnostic to context, and we wanted to see, like, the whole point is to see whether this context helps or not in generation, to make you more informed generation in some sense. So we picked the best model for the context informed kind of models, and the model which does not have access to context.
Would you want again wrong information, or rather correct wrong information, say in the Wikipedia article as the date wrong?
Mm-hmm. It will do the second part, because so the way the task is set up is that you just have to generate one sentence which fits this. You don't actually change the existing Wikipedia article. That's a much harder problem. Okay, so I'll go to the last part of the talk, which is on structure, that is generating longer sequences in a coherent manner. So here is an example of a Wikipedia article which is on the LGBT rights in India, and I'm showing you excerpts of Wikipedia only on one section, that is the contemporary times. Before that you have the history, etc., etc. So as you can see, this is structured in a timeline fashion, where you have starting from 2003, the events that happened in 2003, it talks about that. Then in 2009 and 2012, and then something important happens in 2013, and it talks about that in great detail, that the Supreme Court set aside the 2009 Delhi High Court order decriminalizing consensual homosexual activity within its jurisdiction. You already know what happened in 2009 in this case, and this is what happened in 2013. It discusses that in detail, and then about events that happened in 14, 15, and 2016, and then finally in 2018 it talks about the final verdict that the court unanimously ruled that section 377 is unconstitutional, as it infringed on the fundamental rights of autonomy, intimacy and identity, thus legalizing homosexuality in India. It then talks about the courts of some of the judges that were involved in this decision making process. But now let's have a look at a news article on the same topic, a news report on this particular judgment, and how is that structured. So first, in the title and in the very first two sentences, it will tell you about the ruling. It will not tell you what happened in 2009, what happened before that, etc., etc. It will not even explain what is section 377 in detail. It will then talk about what the judges said. You still don't have a context of what happened in the past that was overruled, etc., etc. And then it will talk about what is section 377, and then finally it will talk about how did we get to this point, the history, what happened in 2009, 2013, etc., etc. So as you can see, it's a reverse order in some sense. It's an inverted pyramid structure. It's very different compared to the Wikipedia article, and these are the kind of structures that we want to capture when we want to generate longer documents. I will talk about some prior work on this topic. The first one is learning structured text representations. This is a hierarchical model. You have word embeddings x1, x2, x3, and x4. And you decompose them into two parts: the semantic part, which is in green, E1, E2, E3, E4, and the structure part, which is in orange, D1, D2, D3, D4. And you calculate structured attention on the orange part using matrix tree theorem. This is explained in the paper. And then you combine it with the semantic part to get one representation of that entire sentence, V1. Now, if you had 4 sentences in the document, V1, V2, V3, V4, you get the representations of those sentences in this manner. And then you apply the same technique to get the representation of the document. You decompose it into the structure and the semantic part, and then finally get a vector Y, which is used for document classification. So there is no supervision given about what kind of structures you have to learn, but it definitely gets a signal in the form of whether the classification was correct or not based on this structure.
How do you get the semantic and structure representation?
Semantic what?
And structure representation?
Oh, they just, so you have this x1 and you have two functions which will transform x1 to e1 and d1 separately, and then you learn the weights of these. There are other models which have also explored hierarchical architectures, but none of these models actually evaluated and saw whether hierarchies are even required to understand document structures or not, and how much do hierarchies help in this. So there was another paper at NACL this year which was evaluating the first model learning structured text representations on 5 tasks of document classification, and it found that if you remove the document level attention, that is the second part of that model, then it does not change the accuracies at all. In fact, for the task of debates, if you remove, then you get much better accuracy. Only in the task of writing quality with topic control does document level structure helps and gives you a better accuracy. But for all the other 4 tasks, if you remove this attention, then it does not affect the accuracy of the tasks. And they also do some other kind of evaluations, like what are the tree heights, the trees that you get from these structured attentions, what are their heights, how much % vacuous trees do you get. Like vacuous trees is when you pick the first 2 or the last 2 sentences and all other sentences are the children of this, which will be, that means your tree will be of height 2. And as you can see, for all the 4 tasks, you have tree height of 2. And for the same 4 tasks, you have very high % of vacuous trees, you have very high proportion of leaf nodes compared to the all the number of nodes that are there. Only for the topic control task do you have a tree height of 4, and for that you can see that the vacuous trees are also lower, etc. So this paper kind of concludes that this model does not learn structure effectively. We don't know whether structure is actually required to solve these tasks or not. So my questions would be, does structure help in generating documents? And do we need hierarchical architectures to actually capture these structures, these state transitions or not? And the most important question is, how do we evaluate even if we are able to learn structures? The techniques that I have just described, which are by other models, other papers, they use rhetorical structure theory to compare whether the model has actually learned structure or not. But the examples that I showed you in the first 2 slides don't really apply to this kind of theory, because I'm looking for something more higher, more like topic transitions or state transitions in the document. So rhetorical structure theory may not be the right way to evaluate for me. And so this is my ongoing work, on trying to learn structure and trying to generate documents using structures. But one of the other small projects that I have done, this is my intern work this year, is on trying to understand dialog structures. This fits into the structure part of my work. For dialog structures, when we have conversations, all of them also have some kind of structure. You're trying to elicit some information, you're trying to make your point in the conversation. For example, today I met a couple of people in the morning in my meetings, and they wouldn't come and just ask, I read your paper and explain me how did you do this. That's not how you begin the conversation. It's like, hi, how are you doing? Did you like Amherst? Did you have a comfortable night? I read your paper, it was very interesting. And the moment you listen to that it's interesting, you know there's going to be a question coming on that. So you kind of try to segue the conversation in trying to achieve what you want to achieve. So you do have a goal when you're having that conversation. You want to know some information from this other person that you're talking to. But goals are very implicit in the conversations that you have in everyday life. And also there are no good data sets which actually annotate. You have annotation of, oh, this was the goal that was of this entire conversation or something like that. But what if you had a data set which had such goals? So there is this data set which has which gives you a setting. That is, it tells you where the conversation is happening, whether it is happening on a beach, in a school, in a temple, or in a castle. You have that information. You have information on the personas of the 2 people who are having the conversation. So whether you are talking to a king or a queen or a knight, or even in this data set you could talk to dogs and cats and rats and everything. So you have the persona, and you also know whether you yourself are an evil king, or you're a just queen, or you're a loyal dog, who are you? So it also has this aspect of the persona. You have objects that you can use to interact with people, like the king has a crown or a scepter, the dog has a stick, and so on. You can take actions with the other characters, like you can hit someone, you can hug someone, you can give food to someone or give toy to someone, etc. And you can also emote, like you can smile, you can cry, you can ponder, etc. And the most exciting thing is that all of this is in text form. None of this is in images, emotes, no emojis. The actions are taken in the text form, the objects are in text form, the emotes are in text form, everything is in text. It's the light data set. This is a paper at EMLP this year. And it is a stateful game engine, which is also very important. So basically, when you take an action, you can actually execute it in the game engine, and the state of the game changes. So if the king gives away the crown to the servant, then he cannot keep giving away the crown, because he had only one crown, and which he gave away. So it's a stateful game engine, and this helps in trying to set up the task. So now that we have all of this rich environment and information, then how do you use it to understand dialog structures? So you have to define a task on this data set where you can actually see whether you're learning dialog structures or not. So you have an agent which can talk, and this agent is given a goal to achieve. And there is another agent which can speak and act. And the goal of this agent is to make the other person actually do an action or an emote. Like you have to say something, this agent has to learn to strategize and say something to the other agent, such that that agent actually performs the action which this agent wanted it to do, or emote in a way that this agent wanted it to do. Like it has to make it smile, then it will tell it a joke, and things like that. So we use reinforcement learning model, where this is your RL agent which you have to learn, and this is the environment agent which is pre-trained on the human-to-human chit-chat data set. So it knows how humans would act in this situation. If this RL agent says something, it knows whether it has to act in a particular way or not. And so you can have this dialogue back and forth between the RL agent and the environment agent until your number of steps are exhausted, or until your goal is achieved, and you get reward based on whether your goal is actually achieved or not. So the reinforcement approach that we use is that the policy has to learn to pick the correct topic of the next utterance, such that the goal is eventually achieved. That is, you are looking at topic transitions so that you achieve the goal at the end. You are learning to strategize. So as an example, this is an example of what we want to see. Like if the RL agent is the king, and it is talking to a queen, which is the environment agent, and it knows the setting and its persona, etc. But the goal for the king is to say something to the queen such that the queen hugs the king. And the strategy that it used is that it flattered the queen. The king said, "Hello, my queen, beautiful as ever," and the queen got happy and hugged the king. So this was the goal, and which it achieved by using this strategy. So here are some results on this model. The inverse model is the model which does not learn to strategize at all. It doesn't do any kind of dialogue planning, etc. It is just trained on human-to-human chit-chat. The topic RL is the model which is trained to pick the correct topic such that you reach the goal eventually. And the top KRL model is the one where the policy learns to pick the right utterance given 20 top utterances, or K number of top utterances. We have tested it in two settings. We have two goal types, first of all, where you have to make the other person actually take a particular game action, or make it emote in a certain way. And we have tested it on 2 settings, where scene settings, where the model has seen some of those settings before, but it has not seen the actual dialogue, and test unseen, where this is on settings which it has never even seen before. And we have 2 metrics. The first is reward, of course. What is the average reward on some number of test set examples, and the average number of turns. So how quickly are you achieving your goal? Do you need 3 turns to achieve your goal, or do you can you achieve it in a shorter number of turns? So as you can see, across board, topic RL model definitely performs much better than the inverse model, which tells us that actually strategizing does help in generating better or coherent or on-topic responses. And so bringing us, this is the last slide of my talk, bringing us back to this unified model where you can do all 3, style, content, and structure. You can control all of these 3. You can imagine this even in the setting that I just described, where I was trying to control for the structure that leads to goal completion. You also have information on persona in that data set, so you can imagine generating sentences that belong to a particular persona, and you can also control for the content. That is, you have to say things that are relevant to your surroundings, to your settings, using the objects that are given to you. You cannot talk as if you're on the beach when you're actually at a temple or something like that. So that is what I would like to build eventually. So I want to thank all of my collaborators, especially my co-advisors, Alan Black and Ruslan Salakutanov. I noticed that when Raj was introducing me, he just said Ruslan and Alan Black because his last name is a little hard to pronounce. Ruslan Salakutanov. Okay, thank you. Do we have any more questions? Yeah.
Okay, a small question. When you were looking at all of the trees that, or I guess not your work.
It's not my work, yeah.
Right. Was there any also comparison to this, like right branching or left branching trees?
No, I didn't see it, that in the paper.
Yeah, and also the differences that you showed in that table were relatively small. I suppose they could also be explained by just variance of these models. Like it might not be the case that any of these differences are having any impact at all.
But I mean, the point of the paper was that it's not learning good trees. So, yeah, like, so.
Yeah, I'm just saying that all of those models could have been doing basically the same, and it could be explained by just some random.
Yeah. They didn't compare multiple models, actually. It was just one model that they were trying to evaluate, the learning structure text representation model. The other models they have not compared. They've just tried to understand what that model is learning. Okay.